Now that we've seen how linear algebra gives us a insight into the coloration properties of a matrix, as long as we know how many colors we're trying to use, we know how to develop a linear algebraic strategy for determining whether or not a diagram is k colorable with that many colors, k. But what we want ultimately is not to have to ask individually about each number of colors we could possibly use. We want a single sort of master invariant, like a Rosetta Stone, that tells us about all the coloration properties, not just for a single value of k, but for all possible values of k. So to do that, we have to get a little bit more general and bend our argument just a little bit in order to get there. We're going to have to sacrifice a couple things along the way, unfortunately, because we end up starting to break some of the additional symmetries that we had in the process. I'll explain a little bit about what that means to get us started. But at the end of the day, what we're able to do in this process is develop a matrix that's another sort of D by D matrix with as many rows as there are crossings in our diagram and as many columns as there are arcs in our diagram, right? So same shape of a matrix as we've been working with today so far. But the entries of our matrix are no longer just going to be simple integer residues modulo k, where k is the number of colors that we want to use. Instead, our entries are now going to be polynomials with a single indeterminate variable that we're going to call t, right? So I'll have to explain how it is that we can use polynomials to bend the rules here a little bit, and then what we have to sacrifice along the way. But we're going to get a matrix that looks very much like the coloration matrices we've already been building today. It's just instead of having a pair of 1s and a -2 in each row, it's going to have these carefully selected expressions involving t's in them. And then getting coloration information out of that matrix, we're just going to do it in a slightly different way. Rather than row reducing it, or trying to row reduce it to test for how many solutions it has, instead we're going to use a classic computational technique that was really in fashion at the time that Alexander discovered this strategy in the 1920s, 1930s, and that's determinants. So determinants are a way of telling whether or not a matrix equation has solutions, and if so, how many, just by grinding out a polynomial expression in the entries of that matrix. So we just sort of put it into this determinant machine, we turn a crank, we get this polynomial nasty looking thing out of it, and the properties of that polynomial tell us about the nature of the solution set of that matrix. Right? So we're using a polynomial to kind of stand in for the question of what kinds of solutions does this matrix equation have. And that polynomial that we get in this process is called the Alexander polynomial. So how does it work? What do we have to do in order to bend the rules and sort of expand our horizons away from the specific k coloration matrix that we've already seen today into a Rosetta Stone matrix that has all coloration information at the same time? The first thing we do is we expand away from this idea of averaging that we started out with. Remember, we powered our k coloration questions using this averaging process. The overstrand is the average of the two understrands, right? And that had this really nice magic property, right? The fact that it was an average is what made it so that either all three of the numbers involved had to be the same, or all three of the numbers that were involved had to be different, right? So averaging is what made this approach magical. When we took the first step from 3 coloration away into 4, 5, 6, k coloration, the first thing that we sacrificed is the threefold symmetry, the ability to completely not tell the difference between the 2 under arcs and the third over arc, right? As soon as we wanted to try for 4 coloration, we had to make a distinction between which arc was the overcrossing arc and which 2 were the undercrossing arcs, because -2 was no longer equal to +1 mod 3. Right? And so the over arc, which got the -2 coefficient in this equation, had to get a different coefficient than the other 2 arcs. So as soon as we went from 3 coloration to different than 3 coloration, we already lost something in that process. We had to now distinguish between the over arc and the 2 under arcs. But the 2 under arcs in this equation are still indistinguishable from one another, right? If I trade places with the x and the y, if I make this y plus x instead of x plus y, that actually doesn't change my equation, right? The role that x is playing, the role that y is playing are completely analogous, even in this k colorability equation. As long as we label which one is the overcrossing, it doesn't matter which undercrossing is which, is what I'm trying to say, right? Because they both have the same coefficient of 1 in this equation. So we can't tell if you trade those places out. Unfortunately, we're going to have to abandon that as well. okay, in order to get to where we're going. And here's why. So the strategy that we're going to use is to replace an averaging process. And in an averaging process, the two things that I'm averaging are each equidistant from the average, which is at the midpoint of the two of them, right? 2 and 8 are equidistant from 5, which is their average, right? They're both 3 units away. That average is exactly halfway in between the other two, which is why we get the symmetry that we get with this, right? Because the average is exactly halfway in between, so the distances from the average to each of the two numbers that that we're averaging together is equal. The first thing we do is we bend that a little bit and say we can still have a magic equation-like feature as long as we know that my average, quote unquote, is somewhere in between the two endpoints. It doesn't have to be exactly halfway in between, but it has to be maybe t% of the way from one of my numbers to the other one of my numbers. And as long as that t is somewhere between 0 and 100% of the way, right, we know that those 3 numbers are either all going to be different or those 3 numbers are all going to have to be the same. So that's the place where we push first to try and become more general. Instead of insisting that the overcrossing arc is exactly halfway in between the values of the two undercrossing arcs, we say, well, it's somewhere in between. And that somewhere-ness is encoded in an indeterminate variable that we call t. So what we say now is that the overcrossing arc, this f of x sub k here, is going to be 100 times t, whoops, this is a typo, 100 times t% of the way between the first color and the second color, right? And that t is some variable whose value is between 0 and 1, exclusive of 0 and 1. And so the way to do that is we form what's called a convex combination. T times the first color plus 1 minus t times the second color is equal to the third color, right? Where the first and second colors are the colors of the under arcs, and the convex average is the color of the over arc. Right? So that's where t comes to the table, right? Is that we're now using it to represent this sort of unknown amount by which this overcrossing color lies in between the other two undercrossing colors. But what this also does is it breaks the symmetry between our two underarcs. I can no longer trade places between one underarc and the other underarc and get the same equation, because one of them has a coefficient of t, the other one has a coefficient of 1 minus t. So if I trade my two endpoints, what used to be 25% of the way along the line will now be 75% of the way along the line instead, right? So my average is my new kind of averaging, weighted averaging, is going to change because I can tell the difference now between the colors of my two endpoints or my undercrossing arcs. Okay. So what that forces us to do actually is it forces us to completely think differently about what kinds of knots that we're studying, because in any ordinary knot diagram, we actually can't tell. There's not a consistent way for us to tell the difference between the two undercrossing arcs that are incident at a crossing. And so what we have to do, this is a pretty major concession, but it turns out not to be too bad to work with in practice, is that we have to give our knots an orientation. We have to give our diagrams an orientation. We have to say, we're going to study this diagram by driving a car around this diagram in a specific direction, right? And so, for example, one way to do it would be to just kind of draw some arrows, as if to say, I'm sort of driving my car underneath this bridge past this crossing, right? So I'm going this way, and then I do some other stuff in my knot, and then I end up coming back to this crossing on my overcrossing arc. And so this overcrossing arc is going to have an orientation associated with it as well, right? So setting an orientation down on a knot is nothing more than taking its diagram and just saying, we're going to trace this diagram around in this order, right? And sort of draw little arrows on each arc that sort of show me which way my little car is driving along the diagram. We're going to need to be able, and this is another sort of little bit unfortunate part, we're going to need to be able to tell the difference between a crossing that happens like the one that I've labeled here versus a crossing that happens with the opposite orientation, right? Same direction for my undercrossing happening, but a different direction for the overcrossing that's happening there. So we're going to need to make a distinction between those two, because now that we've set an orientation on our knot, those are no longer the same situation. And so we develop what are called positive crossings and negative crossings. And we decide that the rubric that we'll use to evaluate which crossings we call positive and which crossings we call negative is that if I'm driving in a little car underneath this bridge, right? So if I'm driving, let's say, this way from bottom to top along this undercrossing. I look at the traffic that's passing me on the bridge as I go underneath the bridge. If the traffic is passing from my left to my right, so that's what's happening here at this positive crossing, then we call that a positive crossing. On the other hand, if I'm driving underneath the crossing and I look up and I see the traffic going from right to left, as is in this diagram on the right here, I call that a negative crossing instead. So if we want to work with oriented knots, we also have to have oriented crossings, and this is how we decide which crossings we assign a positive orientation and which crossings we assign a negative orientation. And as you might expect, the difference between those two things is a difference between a t and a 1 minus t, in a way, right? It's a difference between which arcs are undercrossing in which order. Or another way to see it is it's a difference between the indeterminate variable t and the multiplicative inverse of t, 1 over t. So actually the difference in the algebra between what we do at a positive crossing and what we do at a negative crossing is that at positive crossings we use the variable t and 1 minus t for my undercrossing arcs. And at negative crossings we use t inverse, or 1 over t, to build the crossings at those. And so these two equations that are above me, 334 and 335, this gives us the recipe for how to build the matrix, which is going to encode all of the crossing data for an oriented knot in a way that has, first of all, bent our insistence on having an average that's exactly halfway in between the two. It's relaxed that, so we can use t to represent that unknown how far in between the two extremes that our average lies, and also gives us a way of encoding positive crossings differently from negative crossings. And so if I do that process, I get a matrix that has one row for each crossing and one column for each arc in my diagram. And at each positive crossing, the incoming under arc gets a t coefficient, the outgoing under arc gets a 1 minus t, and the bridge, the over arc, gets a negative 1 coefficient. At a negative crossing, the incoming under arc gets a 1 over t, the outgoing under arc gets a 1 minus 1 over t, and the bridge arc again gets a negative 1 for its coefficient. But that gives us a recipe for building a matrix that we call the Alexander matrix for our knot. We can show that, like the coloration matrices that we've been working with today, it's a knot invariant as well. And so it represents the knot. It doesn't just represent the diagram. Any diagram for the same knot is going to have the same Alexander matrix at the end of the day. And the properties of that matrix can tell us about not just k colorability, which is what we would get if we set t equal to 1/2 and did all the linear algebra mod k, but if we leave t as t, it has the ability to represent sort of all that structure simultaneously, right? So just to walk through an example, this is the example that's here in the textbook page, but here's what it kind of ends up looking like. We take a knot. Here's a knot that has 5 crossings, and I have started with a knot diagram, and then the first thing I did is I just assign an orientation to the knot, and I did that just by drawing these little arrows in here. So the orientation I'm choosing is that we're going to follow the knot around in this fashion. So it's like my kids playing Super Mario Kart, right? We're just going to take one lap around this course and just label which direction that we were going. And so that gives each of the arcs in this diagram a direction also. And so then at each of the crossings, we can see which arc is the incoming under arc. In this case, it would be the arc I've labeled C at crossing 5. The outgoing under arc is what I'm calling D. And the bridge arc is the arc that I'm calling E. So we know that we're going to have C, D, and E playing a role in the equation for the validity of the coloration at crossing number 5. And also, we have to decide whether it's a positive crossing or a negative crossing. And so I get in my little car, I drive in the direction that I've oriented my arc, and as I look up from my car, I can see the traffic going from left to right over the bridge. That makes this a positive crossing. In fact, in this particular diagram, if you follow everything around, you'll figure out that with the orientation I've given it, actually all the crossings in this end up being positive crossings. But of course, that might not happen in a more general situation. So every time you have a positive crossing, we'll use this positive crossing equation. From up here we go. We'll set up this equation. If we encounter a negative crossing, we use the negative crossing version instead. And so in the process, we build these 5 equations, right, that tell me again the incoming under arc gets a t coefficient, the outgoing under arc gets a 1 minus t coefficient, and the bridge, the overcrossing arc, gets a -1 coefficient. And at the end of the day, we end up building this matrix where each row has a t in it, a 1 minus t in it, and a -1 in it, depending on which is the incident undercrossing, the outgoing undercrossing, and the bridge, respectively. Right? And since all my crossings are positive, all of my t's are t's instead of 1 over t's. So I get this matrix, this nasty looking matrix. That we know for sure, this matrix is also going to, because this matrix equation is always going to have a trivial solution. We can always color any diagram with all the same color and get a valid solution to our system of equations. We know for sure that this matrix also will definitely be not invertible. Because if this matrix were invertible, there would be a unique solution that's trivial, that would be all zeros for this, and that would be the only solution possible for this matrix equation. But since there's always a non-zero and yet trivial coloration solution, we know for sure this matrix is not going to be invertible for sure. What that means is if I take the determinant of this square matrix, remember the determinant of a matrix tells us whether the whole matrix is invertible by telling us whether or not that determinant is equal to 0. If the determinant of a matrix is equal to 0, that means that the matrix is not invertible. And conversely, if the determinant is non-zero, the matrix is invertible for sure. Right? So the determinant of a matrix is one of the things that it is. It's an invertibility test. Right? If the determinant is non-zero, the matrix has an inverse. If the determinant is 0, the matrix definitely does not have an inverse. And so we know for sure this matrix will definitely not have an inverse, and therefore this matrix guaranteed to have a determinant of 0. So that would seem to make determinants not a very useful tool for studying the properties of this matrix. And that's almost true. In order to get some useful information out of this matrix, then, what we do is we have to start looking at its submatrices. So the whole matrix is going to have a determinant equal to 0, always, for any knot when we build its Alexander matrix, determinant is 0. But if we cross out one row and column of this matrix, so let's say we take the first row and the first column and we just get rid of them. We're going to get a 4x4 matrix instead of a 5x5 in this example. And that submatrix actually probably does have an interesting determinant. It's probably not just equal to 0, because that submatrix probably is invertible. We can find interesting solutions to submatrices if we just forget about an arc and a crossing, basically, and ask about the rest of the knot diagram. Can we get something interesting there? So that's kind of the philosophy of how this all works. And if we just cross out one row and one column of the matrix and then take the determinant of what's left, we're going to get a polynomial that is a member of what's called the first Alexander ideal of this knot. Fancy terminology. But here's what it ends up looking like. So here's my Alexander matrix. And I can pick any row that I want to and any column that I want to and just delete them, throw them away from the matrix. And then take the determinant of what's left. So if I pick the first row in the first column and I take the determinant of what's left, that's this matrix, its determinant gives me this polynomial that's down here. And that's not 0, right? So this 4x4 matrix actually is invertible for some values of t, right? That makes this determinant not equal to 0. Okay, but what if I pick a different row and different column? It looks like that determinant, the matrix is different, but the determinant looks pretty similar to what I had before, right? Let's take a closer look. It looks like the only difference between the determinant when I took away the first row and the first column versus when I take away the second row and the first column, the only difference in those determinants is a sign of -1, right? This determinant is just the opposite of this determinant. Let's try removing different rows. So something really interesting is happening here. It looks like all the determinants that I get by removing one row and one column from this Alexander matrix, they all look like they're almost exactly the same. The only difference between them is that some of them are just multiplied by -1 compared to the others. And that was Alexander's discovery in this, is that when we build this matrix from an oriented knot, the determinant of the whole matrix is always 0. But anytime I remove just one row and just one column and take the determinant, all of those determinants that I get from that process of removing a row and a column, those are all going to be proportional to one another. They're always going to be a multiple of one another. The first Alexander ideal consists of all of the multiples of the polynomials that we get in this process. Right? And all of those multiples can be explained as multiples of a single generating polynomial for the ideal. And that single generating polynomial for the ideal is called the Alexander polynomial for this matrix. So that was a big mouthful. And so let me just explain where we get that one single generating polynomial from. So we notice that all of these determinants that we get are all multiples of 2t minus 3t squared plus 2t to the third power, right? We get either it or we get -1 times it. Right? That's all that we're getting here in this process. But that polynomial itself is also a multiple of a simpler polynomial. Right? I can take and factor out a t from all three of these terms. And if I factor a t out of all of those terms, I can explain all of the multiples, all of the polynomials that we get by taking these determinants as a monomial multiple of the polynomial that we get, which is just what I get when I factor a t out of this. 2 minus 3t plus 2t squared. Okay. That polynomial is what we call the Alexander polynomial for this matrix, or for this knot. So the rule of thumb is whatever polynomials we're getting from that process, we just want to choose that polynomial which has a positive leading coefficient, right? So we don't want to choose -2t to the third power, right? We want to first flip the sign of that coefficient so it's +2 instead. And then we want to factor out as many powers of t as are necessary to make the degree of this polynomial as small as possible. So here, as soon as I factor out a single power of t, we find that there's a second order polynomial, a quadratic polynomial, which explains the set of all polynomials in this ideal. Right? So the Alexander polynomial is the polynomial of positive and yet minimal degree, which has a positive leading coefficient, and which generates the principal ideal, which is the first Alexander ideal, obtained by the determinants of the one row, one column deleted Alexander matrices of the oriented knot. So because that data is obtained from a matrix which is an invariant for the knot, that means that this polynomial is also an invariant for the knot. And if you look through a catalog of knots and their Alexander polynomials, so here in my table of knots, what we can see is that all of these different knots, so 3 crossing, 4 crossing, 5 crossing, 6 crossing, I mean, this database has a bunch, but they all have different Alexander polynomials. Because the Alexander polynomial is a knot invariant, it means different knots probably have different Alexander polynomials. But I'm hedging there, because in fact, Alexander polynomials are still not a complete invariant for knots. There in fact do exist complicated examples of different knots that have the same Alexander polynomial. But we know for sure that if the Alexander polynomials differ, that we know that the two knots must be different. Right? So it's an invariant, so it can discriminate between knots. It's an invariant, so when it's different, the knots are different. But it's not necessarily the case that when the knots are different, the Alexander polynomials are different. But it's pretty powerful. You have to work pretty hard to come up with an example of two different knots that have the same Alexander polynomial. So for example, that one that we were just looking at, the Alexander polynomial for the knot we were just working on, 5, 2, is 2t squared minus 3t plus 2. So there it is in this list. And so what this can allow you to do, and what I'm asking you to do in this third question of the assignment, that I guess I'll have you work on independently if you like, is once you have an unknown knot, so somebody comes up to you on the street and hands you a diagram of some wadded up string, right? We want to figure out what knot is this thing that they handed me. We can go through this process to construct the Alexander polynomial for that knot. And then once we know the Alexander polynomial, we can come to a field guide of knots like this one that's behind my head right here, and just sort of look down and see, well, which knot has the same Alexander polynomial as mine? Because chances are it's the same knot. We can't be 100% positive, but at least it can give us a clue as to where we could start looking for other knots that are in fact the same as my knot, even if the diagram is quite different. Right? And then that might give us a way to say, well, can I find a sequence of Reidemeister moves, untwists and do-si-dos and all that stuff, right? Can I find a sequence of moves that take me from my complicated diagram to the diagram of this simpler knot that has the same Alexander polynomial as mine? Because chances are the answer is yes. So the Alexander polynomial invariant is super powerful way to do it. And it just arises out of these questions about coloration. that we started today. As soon as we make coloration into linear algebra, and then make an average into a convex combination using t and 1 minus t, and as long as we orient our knots so that we can tell the difference between those two, then the matrix that we get in that coloration process, its first subdeterminants, the determinants that we get by deleting one row and one column, are enough to tell me about a polynomial invariant that is going to discriminate between different knots. I should mention, too, that we don't, because of this theorem of Alexander's, right, we don't actually need to compute all of these different determinants in order to discover the Alexander polynomial, because they're all multiples of one another. So all we have to do is find one. Any subdeterminant that you want to. Remove any row, any column, it doesn't matter which one, just do one, and then take that polynomial that you obtain in that process and make its leading coefficient positive, so multiply by -1 in this example, right? And then divide away as many powers of t as are necessary to give it a positive minimal degree, which in this case is just factor out 1 power of t and take what remains. And that's how we can compute the Alexander polynomial for a knot.